Now let's talk about cost. Recursion is not free. Its price is measured in frames of memory, not just in steps of time. This table compares two recursions. Factorial of n takes big O of n time. The calls descend all the way to 0. Its space is also big O of n, because n plus 1 frames are alive at the deepest point. Recursive binary search takes big O of log n time, one call per halving. Its space is big, O of log n2, because the stack is only as deep as the number of halvings. Think of it this way. Time counts the calls. Space counts the frames alive at once, at the deepest point just before the recursion starts to unwind. A function can be fast in time, but still costly in space if it goes very deep. Here is a common trap. You may feel recursion is free because you never called malloc. But every pending call is a real frame in memory. Go n levels deep, and n frames sit in memory at the same time. So recursion's memory cost is its depth. It is big O of n here. For a tree of height h in later chapters, it will be big O of h. Now be careful with two different limits. Counting down from 100,000 stacks about 100,000 frames before the base case, which is deep enough to overflow the runtime stack and crash. Factorial of 100,000 would crash too, but it also overflows the long type long before that, which is a separate problem. Integer overflow and stack overflow are not the same thing. The stack cost is about depth, not about the size of the result. Let's compare three ways to compute factorial: recursive, explicit stack, and a true loop. In time, all three are big O of n, they do the same amount of work. The difference is space. The recursive version uses big O of n on the call stack. The explicit stack version uses big O of n in your own array. But a true loop needs only big O of 1, no extra memory at all. Does the code read like the problem? The recursive version does. It matches n factorial equals n times n minus 1 factorial. The other two do not. Their shape is hand-built. What limits the depth? The recursive version is limited by the runtime stack size. The explicit stack version is limited by your array size, max depth. The true loop has no depth limit at all because it does not recurse. It just keeps a couple of variables. One more point about that last column. A true iterative factorial with result times equals I inside a for loop needs no stack at all. Its space is big, O of 1. The explicit stack version keeps big O of n on purpose. It is there to show you the conversion technique. So do not read it as advice. It is not the cheapest way to compute a factorial. Let us do a quick check. Why is recursive binary search's space big O of log n, while recursive factorial space is big O of n, when both of them recurse until a base case? Pause the video and think about it. The answer is depth. Depth is what sets the space. Binary search halves its interval on every call, so about log n halvings reach the base case. Factorial shrinks n by only 1 each call, so it needs n calls to get there. More depth means more live frames and more space.